So let's take a look at an example of this exploding star. Let's say that we have, the spherical star, mass m, has a certain radius, and a certain angular speed. The star explodes, ejecting mass into space. The star that's left behind has a mass 1/10 of what it had and a radius 1/20th of what it had. And we want to figure out the new angular speed of the star as compared to, what it started as. So when we consider this situation, we can go ahead and draw this out, and that'll help us visualize it. We have, our spherical star here. We have the smaller one. That's the result. 1/20th of the radius and 1/10 of the mass. And so we know that the moment of inertia for a sphere is 2/5 mr squared. And what we can do is we can set up a ratio of the new situation of the old to see what's going to happen, because we know that the angular momentum still must be conserved. And so, we have the same, again, same angular momentum. The drop in the moment of inertia, well, really the change, right? So we know that the mass is changing, and we know that the radius is changing. Both of those have an effect, and we want to figure out, okay, what's going to happen to our angular speed. And so, in terms of increasing or decreasing, right? So let's set this up. 2/5 mr squared, we have m over 10, and then r there over 20. And then we have the, again, the new situation divided by the old, so new over old. And 2/5 will cancel from both sides, or from the top and bottom. Mass will cancel from the top and bottom. If we square, we have to square the r and square the 20. So 1/10 r squared over 20 squared. And then that's over r squared. The r squareds will be gone. And when we multiply those together, the 1 over 10, the 1 over 20 squared, we have 1/400th of I. So what ends up happening is the angular speed must increase big time. It must increase by a factor of 4,000, which is much faster than it was before. The radius is much smaller, and the mass is much smaller, and so that's the only thing that will make logical sense there. All right, so let's say we have a disk, and it's rotating about a vertical axis with a angular speed, and let's say that we have a piece of clay that lands vertically on the disk, and it attaches 0.25 meters from the center. We want to find the new angular speed of the disk. So in this case, right, it's spinning, and essentially what happens is, we have this mass fall on it. So we know that conservation of momentum, momentum is conserved as long as there's no outside forces, right? So we can actually consider this mass and this disk, the momentum being conserved before and after, and therefore we can find the new angular speed because of this change. Now, if we think about it, right, this is rotating around. This has a certain angular momentum, right? When this mass falls on here, this system now has a different moment of inertia. I is different, and I is just increased because we have more mass, right? And so that I is changing. Therefore, the angular momentum must change. And so if we set up, the momentum before, the momentum afterwards, which is, I omega before equals I omega afterwards, we can find the new angular speed. So, if you look at your reference sheet with the disk and with just a point mass, beforehand you just have the disk. Afterwards, which is, this is the disk. Afterwards, you're going to have not only I is going to be not only 1/2 mr squared, right? But it's also going to be, you're also going to have to add the moment of inertia for a point mass, and then times omega. So why don't you go ahead and figure out what the final omega should be if you know the initial initial angular speed, and that'll be good. All right, so let's see how you did there. So we have the I before, I after. We know it's the same final, the same for both of them afterwards. So we add up both, just like you saw there. So we have those together, and we should end up getting 2.72 radians per second, and that is the final angular momentum, or the angular speed. And it's slower, right? So it started at 3.6, and it has to be slower because the moment of inertia has increased.